Okay, it's the 6th of May. Resist! That's my little joke. Okay, some of you are not into resistance. So resistance is opposition to movement of charge. This is like friction for electricity. And there's a formula for this. So resistance equals the potential difference, which we know is voltage, divided by actual current. It's measured in ohms. You already got a lot of this, hopefully, from the videos, because we're going to be doing some resistance work. So 1 ohm of resistance is 1 volt divided by 1 amp. You know, the other metaphor that we use for voltage, and I don't ever hear it called this anymore. When I was a kid, my dad used to talk about voltage as electromotive force, EMF. And, you know, the metaphor was that voltage was like how much force it took to push something through. Well, then if you think about resistance as a form of friction, the amount of force it takes to overcome that per unit of flow kind of makes sense, but we'll leave the metaphor alone for now. So we will do some calculations with resistance, and they will, well, what we talk about is ohmic versus non-ohmic materials. So Ohm's Law is, you know, all the kinds of resistance problems that you've done in the past. You know from your study of chemistry, from everything else, that some materials conduct current really well and some don't. And those that do conduct we call conductors. I'm sure you, yes. I'm sure you meant to say conductors. And those that don't we call insulators, yeah. So we have insulators on, you know, you've handled insulators every day of your life if you've plugged something in. The material that covers an electrical cord is insulating material. Because if it wasn't, what would happen? You'd get zapped every single time, yeah. And if you've ever had the misfortune of plugging something in where the insulation on a wire was worn and you've gotten zapped, you know that insulation is really important. For most materials, the amount of resistance they have is some constant number. It's some constant number of ohms. We can determine the amount of resistance in a material. Those are ohmic materials, so their resistance does not change. There are some things that change their resistance, that they conduct differently based on conditions. Any idea what we might call those? I mean, they're non-ohmic materials, but if they conduct selectively, what? Semiconductors, yeah, semiconductive materials. So you talked about that when you talked about like semi-metallics in chemistry, metalloids. A lot of those semiconductor materials are what we call the non-ohmic materials. They change their ability to conduct based on conditions. Okay, as we start our soldering today, we're going to look at some resistors. Different things do affect resistance. So how thick a section of material you need to push something through. You know, for a given piece of wire, it's going to have a given resistance. A thicker piece of wire will have a different resistance. And the longer something, you know, 3 centimeters of wire is going to have lower resistance than 10 centimeters of wire. Is going to have lower resistance than a meter of wire. So the longer a piece of something that you have to push current through, the higher the amount of resistance you're going to face. Now, resistance tends to increase the smaller something is. So tinier wires have higher resistance. The way that this makes sense, if you think back to the metaphor about current being like water flowing through a pipe, it's easier to get the same amount of water to flow through a giant pipe than it is to flow through a tiny garden hose. So the smaller the thing that the current is flowing through, the higher resistance. And higher temperatures tend to actually increase resistance. Years ago, I had a relay on a Ford Ranger go bad. And if the truck was warmed up and everything was at operating temperature, and you shut it off, it wouldn't start again. until everything cooled down completely, and then you could restart it. It would keep running, but it was an electrical relay that when it got hot, basically it wasn't functioning the way it was supposed to, and some of the sort of other things that would have mitigated this effect weren't working. When that relay got hot, the resistance climbed to a point where it would no longer conduct current and the vehicle wouldn't start. So if you forgot and shut it off, you had to like go cool your heels someplace for 20 minutes before you could turn the truck back on. It was a lot of fun.
That was yours?
Yes. Okay, these are actually the kind of problems we will do. So resistance can be used to control the amount of current that flows through a circuit. And you kind of did this in the tutorial video that you saw. We will do sample problem 19B together, and then I will actually assign the practice problems on 703, so let's look at those. Okay, so this is 19B on page 702, and this is just a simple circuit problem. So we're given a circuit that has 120 volts, so this would be like standard household current. This is not direct current. This is an alternating current circuit. And an iron that has a resistance of 19 ohms. Any appliance that heats up is basically a big resistor. And if you think about the metaphor of resistance being like electrical friction, what happens if you drag something across a floor and you generate a lot of friction? You generate a lot of heat. Electrical friction, metaphorically, resistance also generates heat. So like electrical heating elements in an electric stove, they're big fat resistors. An iron is generating a lot of resistance, which causes it to heat up. Okay, so what we have to work with is resistance is equal to delta V over I. We can rearrange that, of course, and we get I equals delta V over R. And we'll have to shrink this. So we want to solve for our amperage. I equals 120 volts divided by 19 ohms. What's your raw number? Okay, raw number is 6.3157 blah, 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 blah amps. We have three sig figs to work with because that was actually 19.0. So we have a current of 6.32 amps. Okay. The most common way to use this, and what you saw in the video tutorial, because usually our voltage, our potential difference is fixed. We can't change the potential difference in a circuit, but we can regulate the amount of current that a particular part of the circuit gets by using the appropriate resistors. So that's typically how we use this. Assigned here are the 19B problems 1, 3, and 5. And I guess we'll grade those the day before Judy Chicago, probably. Yeah, so Tuesday. That's the 12th. Okay, so 19B, that's page 703, 1, 3, and 5. Okay, let's move on. Electric power is one of the things that we're really not going to touch on. I just want you to be aware of it. If you're going on in physics, you will, if you're doing any electronics in physics, so like civil and chemical engineering majors, you probably won't have to do a lot of this.
So do we need this for the test?
No, you're not. I'm just going to talk about it. So you don't remember because we didn't get to it this year. Power is how fast you can do work. Power is how fast work gets done. So it's work divided by the time that it takes to do that work. And electrical power is similar. It's how much you can change the electrical potential energy over a unit of time. And we rearrange everything to find that power is equal to current times voltage. So it disregards resistance in the circuit. And power is actually how like your electric bills are, your billed in for the power you use. Okay, so this is a little bit more about electric power. As I said, when you get, you don't get electric bills. When your parents get electric bills, ask to see an electric bill. The billing is actually in power, so it's in kilowatt hours, and a kilowatt hour is 1,000 watts of power being used steadily for an hour. So that's, no. this is actually where I probably should have had you do the videos, but you saw all the symbols for circuit components in the video, and the page 731 has got all of your symbols to review. You are responsible for knowing all of those symbols. You're going to be able to draw me a circuit. Now, why is that funny? Okay, so this is very much what your tutorials were about, and this is what we're going to start with. Wiring resistors in series and parallel. And you had your challenge problem, obviously. So if you wire them in series, the current has no choice but to flow through one before it flows through the other. If you wire them in parallel, the current has multiple paths. And anytime current has multiple paths, it will take them both. So even, this is one that confuses people. Are those two in parallel? Yes. Because current is going to go this way, and it's going to go this way.
At the same time, it's going to split.
It's going to split. Yeah. Anytime that there are multiple paths for current to take, it will. Like, it won't randomly go, oh, you know what, let's all just go this way, guys. It's not going to happen, okay? If there are two pathways for current to flow through, current will flow through both pathways. And how the resistors are wired, well, it determines the voltage at the end of the circuit. Voltage actually is the thing we can least control. It determines the current across the circuit. We will not get into the big complicated, like, more complicated calculations about circuits. We're basically going to stick at the level of equivalent resistance. Okay, so when we put resistors in series, it's really, really easy because you just add them up. So if this is 1 ohm and this is 1 ohm and this is 1 ohm, your total resistance is 3 ohms. We call that equivalent resistance, okay? Because what we're saying is I could either put, copy. We say equivalent resistance because I could either put this there, or I could put this there. They're equivalent. They're going to give me the same resistance. And that's why we call it equivalent resistance. So some of the problems you did with, like the challenge problem I gave you of trying to get to an exact amount of resistance with a given number of resistors, when you don't have the right resistor, how do you make the resistance you need? Well, you use the resistance equations, equivalent resistance. And we will actually, let's look at 20A together, and then I'll assign a couple practice problems from 20A. Okay, so this is problem 20A, and it's all series resistors. We actually have, and this can go on forever, we actually have 4 resistors in series here. So we're asked two things. We're told that a 9-volt battery is connected to 4 light bulbs with these resistances. Find the equivalent resistance for the circuit and the current in the circuit. We can't change the voltage of a 9-volt battery. It's going to be 9 volts. We could put a different battery in. We could put a 1.5 volt battery in there, but we can't change the voltage of the battery. So first, we're asked two things. One is we're asked for the equivalent resistance, and then 2, we're asked for the current in the circuit. So to find equivalent resistance, of course, this is easy. It's 2 ohms plus 4 ohms plus 5 ohms plus 7 ohms. This is a lot of resistance. So what's our equivalent resistance? Okay, so we get an equivalent resistance of 18 ohms. Fairly high resistance for a little tiny circuit. And now we want to know the current in that circuit. So how much current is actually flowing? How do we do that? Little star, V is equal to IR. Okay, so V equals IR, V divided by R. gives us I, or current. So 9.0 volts divided by 18 ohms gives us 0.5 amps. You have a half an amp of current flowing through there. So for 20A on page 739, 1, 5, and 6 are assigned. Also due Tuesday, 5/12. No. Okay. If we take a bunch of resistors and we wire them in parallel, and we can do this in a bunch of different ways, but like these are all parallel. Okay? The current is going to flow through all three of these pathways. So that is 3 resistors in parallel. Equivalent resistance is a reciprocal relationship, so 1 over, basically the reciprocal of the equivalent is equal to the sum of the reciprocals of all the resistors that are there. You did some of these. Let's practice a couple of these. This is 20B on 743. Okay, so we have another circuit with a 9-volt battery. These are pretty common. We use a lot of 9 volts because they're easy to hook up. And we have 4 resistors hooked up in parallel. A 2, a 4, a 5, and a 7. What we want to know is the equivalent, again, equivalent resistance for the circuit and total current flowing through the circuit. So, to get the equivalent resistance, 1 over R equivalent is equal to 1 over R1 plus 1 over R2, etc. So I'm just going to go ahead and swap in our actual values. So 1 over 7 ohms plus 1 over 5 ohms plus 1 over 4 ohms plus 1 over 2 ohms. And I do love saying ohms.
I like saying numbers. Let's say
Hmm?
9.
9 volt. That's okay. There's been a lot of that going around this morning. Okay, so we've got a raw number for 1 over equivalent resistance. How do we get the equivalent resistance? Yeah, reciprocal of that. So 1 divided by that answer gives us the equivalent resistance. So 1 divided by that, and we get an equivalent resistance of 0.9150328 ohms. Pardon? Okay, but we're not done. At this point, we've got the equivalent resistance. We still need to get the current in the circuit. So twinkle, twinkle, little star, V is equal to IR. Why do I recite that every time? Because I can't remember it otherwise. I don't have a note card. So voltage divided by resistance will give us our current. 9 divided by our answer. So we get 9.8357, etc. amps is our current. Notice that this is much more amperage, so we have much lower resistance. So we have a lot more current flowing through the circuit than we did in the last one because we've got a lot more resistance. Strike that. A lot less resistance, sorry.
2 and 3.
And assigned are numbers 2 and 3 on page 744. Okay. Let's look real quickly at what we would call more complex, extra complex resistor circuits. So we're not going to do the super complex resistor circuits. If we had a lot more time to do this, some of you will see this in the future, some of you will not. And this is actually not a circuit, but it's an inverter. So this is something that would do what? What did we say inverters did? Changed it from, yeah, changed direct current to alternating current. So actually, if any of you have ever been inside an RV, if you've got friends or family or anybody who has an RV, RVs typically have an inverter someplace because during periods when you're not plugged in like at a campsite.
What does that stands for? Isn't there, in like in cars when they have power sources in them and you have to press something that either says DC or DC?
Yes, there's an inverter in there. Yeah, cars that have an AC plug somewhere in the back, because you're running that AC power off the DC battery, off the car battery. Most RVs have a second, or sometimes a second and third battery that will power your appliances when you're not plugged into a power source. And those, that DC source of current in the battery has to be converted to AC to run like your refrigerator and things like that. So, okay, what we will do is just a few little things like this. So, if we have a 6 ohm resistor, let's say we have 3 6 ohm resistors. This is 9 volts. What is the current across this circuit? So when you've got any kind of more complicated resistor problem, any kind of more complicated equivalent resistor problem, the way that you want to solve these is by sort of taking the innermost thing, solving for the equivalent resistance of that, and then working back outwards. So by that I mean these two are in what? Parallel. Solve for the equivalent resistance of that first, and then you very often will redraw your circuit. So I'm going to shrink this.
So we are doing ones like this.
We're doing, yeah, not the most complicated. I mean, the most complicated would make your eyes pop out of your head. This is a simple complex circuit.
So would you do 1/3 plus 6? Oh yeah.
Okay.
Yeah.
So the equivalent resistance of this, 1 over Req equals 1 over 6 ohms plus 1 over 6 ohms. Using the multi-view calculators, remember that you can use the parentheses function to nest all of your equivalents. So, I just put in parentheses, 1 divided by 6, close parentheses, plus parentheses, 1 divided by 6, close parentheses, and that gets you 1 over Req equals, yes, 0.3 repeating, 1 divided by that, you get an equivalent resistance of 3 ohms. So what we would do is write Req 3 ohms. Well, now we just have 2 in parallel or in series. This is in series with this, so the equivalent resistance of the whole circuit is 6 ohms plus 3 ohms. So you have
So you just like 1.
9 ohms.
Or
Huh?
1,
It'd be 1 amp. Yeah, because V equals IR. V divided by R equals I. So yeah, 9 volts divided by 9 ohms, you have 1 amp of current in this circuit. Okay?
Are we going to have to draw these?
Yep.
Okay.
What we just did was an example of a slightly more complex circuit. We're going to I'm going to assign 2 from 20C. Number 1, parts A and C. And it's a circuit that's very much like the one that we just did. I will assign the following option. 2B on here as extra credit. And you can get, because it's a more complicated circuit, you can get up to 1, 2, 3, 4, 5 points homework.
Is the 1A and C assigned?
1A and C is assigned, yeah.
And
2 is extra.
So do 5, 12, yeah. 2B is extra credit. Yeah, if you're going to do it. Actually, you know what? We'll make that 2 points extra credit. Yeah, on the homework grade. Okay, so those are your options. Okay, with that, we are going to start some soldering instructional stuff, and we're going to get soldering.